Okay, so let's talk a little bit about the different optimization methods that are used in training deep neural networks. Of course, they have applications to LLM pre-training and so on, but also just in general training any kind of deep neural networks. So the first, everything is kind of based upon stochastic gradient descent that you already have seen in class. And today we will kind of take a slightly deeper dive. Many of these things are currently still under investigation and they are still kind of being worked on. For example, optimization methods for training very large neural networks, for training LLMs. There can actually be some very active Twitter discussions about what methods are good. Okay. So coming back to the empirical risk minimization framework that we've been using so far, right, is you typically have like a linear model. And the thing to note about the linear model, or in general, some objective, is that when you have a linear model, typically you will have a loss with respect to the true label, right? And this loss is then averaged over all the training points. So the training points here are indexed as xn comma yn, right? So this is, it has this form where you have an average over all the training points, n training points, and then you have basically loss for each of the training data, okay? So you can have either a linear model over here, right, W transpose X, or you can have a more general nonlinear, potentially nonlinear hypothesis, H, which is a function of the parameter that you want to find, the model that you want to find, L or H of W. For example, in regression, right, we've seen that the loss function that we use is squared loss, in various cases where you can have different kinds of losses depending upon things like KL divergence, relative entropy, or cross entropy. Okay. Um, and sometimes this kind of was always the supervised learning paradigm in machine learning, that yn are the given labels from xn. And what actually is really interesting these days, in the last, whatever, 10 years or so, that there is this notion of kind of self-supervised learning. So it's not that you are explicitly given yn, right? But you somehow, the yn is an implicit task that you are given from unsupervised data. So sometimes you will hear about these LLMs and hear that they are kind of unsupervised learning or self-supervised learning, because the decoder LLMs that are coming up basically just try to predict the next word given the previous words, in case that this is a causal LLM. And there, what you basically have is that you have a current sentence, right? So that could be like xn, the current part of the sentence, and then yn would actually correspond to the next word. So, one of the limiting things about supervised machine learning was always like, where do you get the labels for, or where do you get the label data, right? So a lot of human labeling, things like Mechanical Turk and so on spun up. But I think one of the big reasons why LLMs are able to encapsulate a lot of the knowledge in the world is that you essentially get these labels kind of for implicitly or for free, right? So that's actually one of the big advances I think we've had in being able to harness all the data that is over there to, basically create these huge models. Um, so at the back of your mind, you can think about these. These could be basically small models from, doing some small statistical studies or so on, to very large LLMs, right? So the ones that are being released now are where W is in the, billions, if not hundreds of billions of parameters, right? So the one of the first methods that you learn of when you do numerical optimization is gradient descent, right? So gradient descent takes the parameters and takes the gradient of f, right? And if you then look over here, then the gradient of f will basically go to each of the points within the sum, and it'll end up being like the average of the gradient of the losses with respect to w. And then there is a step size. So, this particular, this subtraction or this taking a multiple of this and updating the W vector is not that computationally expensive, but the biggest computation now is in computing the gradient, okay? And if you look at it over here, then this, since f of w depends only on you can actually write it as 1 by n times fnw, where fn basically corresponds to this particular loss. But the thing to note is that each of the fn's depends only on the corresponding training data, xn, comma, yn. So the gradient, like I said, is now also can be written as an average of the gradients for each of the training data. But of course, if you just apply vanilla gradient descent, you actually need to go through all the training samples just to do one step. Okay, so obviously it'll be very slow when you have, millions of samples, or even like if you think about how these LLMs are being trained, they actually have like trillions of tokens, right? So let's suppose there are trillions of sentences over there, right? Or then, of course, there is the other parts which are audio as well as video. So lots and lots of data. So there is really no way that you can now, in this setting, compute the average of the gradient. It's just going to be too expensive, okay? So then you can ask yourselves the question that, look, finally you are interested in computing gradient of the function at this point, okay? Can I basically find the approximate gradient, right? Instead of going through each of these points and summing them up and taking the average, right? I want to find the approximate gradient. And one simple thing that one can do, and this is what is used in stochastic gradient descent, is the notion of stochastic sampling, right? So what you can do is you can basically, instead of taking all your data, right, all your training data, you can sample a small subset of this training data, right? And then you can estimate the gradient by taking the sample mean of the gradients over this small subset, right? So you're basically now, doing the same thing as above. So this is the true quantity that you want to get. And what you say is that, well, I will look at the average, but over a smaller sample of the data, right? So B is the batch, and the modulus of B refers to the size of the batch. And one extreme end could be that you actually take B to be equal to 1. So that means you sample one training data at a time. But if you take this idea, right, this is the idea behind stochastic gradient descent. Okay, just a reminder, the training data is all of the x and y n pairs. Okay, so you can initialize W in some way. This is the parameters. And then you basically do take multiple rounds. And each round T, you sample a small batch B. Okay, and then you will update the parameter. Okay, and I've given this over here. One thing that you will notice is that here there is an eta which depends upon T. So T is a superscript over here, okay? Not a power, right? But a superscript over here. So that suggests that the learning rate actually changes with the steps. So in particular, if when you look over here, right, we actually just had eta over here. Okay, there was no index right? So here we've added an eta t, and we'll see that that is actually very important. Okay. Now, I said, there is an extreme case of B equal to just a single training data. And if you think about it, right, the perceptron, right, was actually an example of an algorithm where you were actually looking at one training data, except there was actually no like clear loss function over there, right? So, but you can actually modify if you're looking for an SVM, you can actually modify to actually get a loss function, and then you can actually carry out a perceptron-like algorithm, and it can actually have better properties. So, and as an example, right, you can do this for logistic regression, right? If you remember the logistic regression case, if we do kind of maximum likelihood, then we get the objective to be this particular value over here, right? So each of these log of 1 plus e to the power minus yn w transpose xn is basically an fnw, right? This is still a linear function, right? But now the loss is not the square loss, but it is like the logistic loss, okay? And then if you instantiate SGD or stochastic gradient descent for logistic regression, you have the same steps as before over here, right? Except now we have a concrete F, right? And we can actually take the gradient, okay? So you look at this over here, and you look at the gradient, and the gradient will be, there's a log function over here, so it'll be 1 divided by the quantity in brackets, right? So that's exactly what is happening over here, right? And if you apply the chain rule, then you'll see that it'll be uh, uh, as given over here. Okay. Sorry. Okay, so let's see. Why does stochastic gradient descent work? I've kind of given you some idea, right? Which is that you're getting an estimator of the full gradient. And what you can show is that it's an unbiased estimator. So in particular, the expectation over all the samples that you end up taking, right, of this gradient estimate, the stochastic gradient estimate, is actually equal to the full gradient, okay? So you can think of each iteration that you have the actual gradient, right? And you have some noise. And since it's an unbiased estimator, this noise actually has zero mean, okay? And that's why the expectation of this will be expectation of the gradient, which is constant, right? Plus expectation of the noise. And since this is zero mean, you get that this is an unbiased estimator, and so you can look at gradient descent or stochastic gradient descent as you are updating with gradient plus a zero mean noise. Okay. Now let's think a little bit about step size, right? Like before I said that if you look over here in gradient descent, you can actually choose step size to be a constant. Okay. And why can you choose it to be a constant? Well, this is typically F is going to be some convex loss, right? And we want to find the minimum, right? So in particular, for example, for convex losses, to get the minimum, let's say for logistic regression, this gradient will actually be zero at the global optimum. Okay, so that means that at the optimal, if you are at the optimal, gradient descent will actually lead to no change in W, right? Because the gradient itself of the function is exactly zero, okay? But of course, if you think about it, right, the fact that this sum at a particular W is zero does not mean that each of the individual components is going to be zero. It's actually not going to be true that each of the individual components is going to be zero, okay? So as a result, when you do stochastic gradient descent, okay, you cannot actually use a fixed step size. Okay, because it cannot converge to a global or even a local optimizer where the gradient equal to zero, right? So in particular, I'm now going to repeat what I kind of just said, that if W star is the minimizer, right? Suppose this is a convex loss, right? Then the gradient of W star, gradient of F at W star is actually going to be zero. Okay? But if B is a strict subset, not the entire training data, then there is no reason for this to be exactly equal to zero. So even if we have the minimizer, even if we are actually at the minimizer, SGD will actually move away from it. So you don't want to keep a constant step size. And so what you should do is that you should decrease the step size to zero. So as t increases, the step size should go to zero. Now, there are various ways of trying to decay the learning rate, right? So sometimes it is done with a polynomial rate. Sometimes it is done with a step decay. So for example, here is a figure. On the x-axis is what's called epoch, which just means how many times you are going over the training data, right? Epoch 1, you go through all the training data, right? Doesn't need to, remember that it's not like a gradient descent step. We can have multiple stochastic gradient descent steps within an epoch, right? But the new epoch is one where you start repeating the training data. Okay, so here you basically are going through the training data about 200 times, right? And you can see that in this particular schedule, you're decaying the learning rate down to zero in steps. So you basically keep it constant for a number of epochs, and then you drop it by a little bit. Okay. And then there are other learning rates. There's something called cosine or cyclic learning rate schedules where you can actually go down, you can go up. Sometimes you keep this peak to be the same. In other cases, you can actually take the maximum LR and kind of halve it at every one of these cycles, right? Because you never know when you actually want to kind of stop. So this is still like a very active, um, um, actively researched, as well as, from the practitioner point of view, there are various schedules that people have found that work well for particular architectures and so on. And many times you will now see in research papers or even blog articles and so on that people will specify, what is the learning rate schedule they use, what strategy they use, and what actually ended up working well. And many of it is kind of the result of experimentation, and not all of it is explainable or done by theory. Although there are some recently good papers and kind of methods that try to do like schedule-free optimization, where you actually try to figure out a schedule in the program itself, and they work well, but not as well, I think, as other learning rate schedules. So we've now discussed stochastic gradient descent, right? And if I contrast it with gradient descent, right, the pros are that it is cheaper computation per iteration. Generally, you see faster convergence in the beginning, right? So cheaper computation is obvious, right? Because you're now only going through a small number of data points. Typically, and like I said, they're faster than. The cons is, it's less stable, slower final convergence, and we've talked a little bit about the step size, and it can be actually hard to tune the step size. So this figure is taken from this particular kind of blog article, right? And it shows the trajectory of um, uh, batch gradient descent, mini batch gradient descent, and stochastic gradient descent. I think stochastic gradient descent, I think the batch size is 1 in this particular example. So you can see over here that, you end up going to the global optimal. In mini batch, it's a little bit of a wavering thing over here. And in stochastic gradient descent, it actually goes like this. That's the trajectory. One of the things that a colleague of mine has always complained that stochastic gradient descent, the name of the method itself is incorrect. So can anybody hypothesize why they're saying that stochastic gradient descent might be even an incorrect name? One of the properties actually that batch gradient descent has, that you can actually show that the loss decreases monotonically. So you're always decreasing the loss. Okay, so for example, I think I showed you level sets for linear regression, right? So these level sets are basically contours of constant f values. Okay, and you're trying to minimize f. And this point over here is, if it's a convex loss, it is basically the global minimizer, where f is minimized and gradient of f is actually 0. So you're always moving from an outer curve to an inner curve. So outer curve to inner curve, and that means that f is decreasing, because you can just think of this as kind of like, if you visualize in 3D, you can think of these as, this as like a bowl-shaped surface, so not necessarily cylindrical. And yeah, not necessarily like that each of these contours is a circle, but each of them is an ellipse. And now you're basically cutting at different y values, right? The y value being the value of the f function. Okay, so that means that an outer curve is a larger value of the loss or of f. Inner curve is a smaller value. So over here, gradient descent you can actually show is going to be a monotonic. So that's why the name, gradient descent. You're descending on f. Every step is guaranteed to decrease the value of f. Okay. And then you can see over here, stochastic gradient does not actually decrease the loss at every step. It's not guaranteed to. It can actually increase the loss sometimes. This is what's happening over here. You're going from an inner level set to an outer level set. Okay? So my friend's colleague's peeve, this is Steve Wright from Wisconsin, and his peeve is that it should actually be called stochastic gradient method. It's not a descent method, okay? But I think he's lost the battle because everybody calls it stochastic gradient descent. People have been too used to calling it stochastic gradient descent. Okay, any questions so far?
Can we call it partial gradient descent? Because based on the gradient that it calculates, is actually trying to descend, but that's not the whole gradient. It's like,
yeah, but that is captured by the stochastic part, right? So
right.
stochastic saying that, it's basically an estimate of the gradient. So it is kind of like gradient plus noise, and the noise is zero mean, right? So that part I think is captured. I think what he was saying is that it's actually not a descent method. So he's actually like, if you look at his slides and so on, he's done a lot of work on stochastic gradient. He'll actually call it SGM instead of SGD, stochastic gradient method.
Interesting.
Yes. Yeah, but it's one of those things where people start, you get a name, and even though the name is kind of incorrect, it kind of sticks. Right? I'm sure that you can come up with millions of, or many examples throughout history of such things, right? I'm talking only about like a particular method, but in life also, right? Any questions so far? Okay, so let's move on to see how you can kind of try to improve stochastic gradient descent. So stochastic gradient descent, as we saw, takes Wt plus 1, Wt. So actually, let's first contrast gradient descent and see how we can improve it. Okay, so gradient descent has this update, right? Wt plus 1 is equal to Wt minus alpha of gradient of f of t, f at w of t, right? So now there is this other method which actually uses momentum, something called momentum, which tries to not use just the gradient of f at wt, but actually uses previous points also, the gradient of the previous points. Okay? So suppose I want to take like an average, right? So one way of doing it is, where you end up taking like an exponentially moving average, is to do the following. You maintain a momentum vector, Vt. Think of beta as some value between 0 and 1. At one extreme, it can actually be 0, right? And you take a convex combination of the gradient and the old value of Vt minus 1. Okay, so let's look at it in a particular case, right? What if beta is exactly 0? Beta is 0, this is 0, this is just the gradient of f, and this is just the gradient of f. So it actually includes gradient descent as a special case. So when beta equal to 0, you get gradient descent. When beta is not equal to 0, you can kind of start expanding it, right? So there is a kind of a recursion over here, recurrence over here, right? Vt is equal to beta Vt minus 1. So I can write it as Vt equals 1 minus beta gradient of f. By the way, you can see the cursor, right? When I highlight, you can see the highlighted.
We can see the highlight. We don't see the cursor, but the highlight we can see.
Okay. You don't see the cursor, but you see the highlight. Okay, good. So then actually I should try to highlight it. Sometimes I forget and I just hover over it, right? So you can see that this is Vt is 1 minus beta. So that's exactly the same term over here, right? And then I have beta. This is this beta. And then I have Vt minus 1. So I can now expand Vt minus 1 because Vt minus 1 is beta Vt minus 2 plus 1 minus beta gradient of f, but not at Wt, but at the previous iterate, Wt minus 1. So you end up getting, this Vt minus 1 is basically 1 minus beta f of Wt minus 1, okay, plus beta square times Vt minus 2, beta square, and then you keep on expanding. Okay, so you can see that, I can take 1 minus beta outside. And if I take 1 minus beta outside, what I will get is gradient of f at Wt plus beta times gradient of f at Wt minus 1 plus beta square times gradient of f at Wt minus 2. So it is geometrically declining. That's why it's called exponential moving average. So it's an average, but it's an exponentially moving average, right? So if beta, for example, is something like half, then it'll decline actually very quickly. Okay, because it's beta square. So the smaller the beta, the more quickly it'll decline. And in particular, if beta equal to 0, then you don't get anything from the previous steps. Okay, so that's kind of the idea behind momentum. So instead of just using the current, the gradient at the current iterate, you also use the gradient at the previous iterates. Okay, so that is the idea behind momentum. And remember, right now we are still talking about kind of gradient descent versus momentum-based gradient descent. Okay, so this is momentum gradient descent. Okay, is you do Vt, just like I said, Vt equal to beta times Vt minus 1 plus 1 minus beta gradient of f at Wt. Okay, again, right now, since we are doing gradient descent, we can actually afford to use a constant learning rate. And then beta is sometimes called kind of the discount factor, right? And like I said, particularly beta equal to 0 means that there's no momentum. It's just the gradient being used. But like we said, can't really use gradient descent or momentum gradient descent for large data sets. And if you're optimizing the sum of these, typically losses, right, then you can basically take the stochastic gradient descent and get like a momentum version of that method. Again, that's not hard, right? All you need to do is you iterate over the steps. At each step, you sample. So this is actually taking exactly 1 point. Okay, you take 1 point and you update your momentum, and then you take a step in the direction of that momentum. This should actually be alpha, t, since the learning rate needs to decrease. Okay. Then there is another notion, which is, hey, I take always the gradient at Wt. Can I actually take a gradient at some other point? Okay, so that is what is sometimes called Nesterov accelerated gradient. Okay, and the idea is you'll see that the formula is somewhat similar, that you have this momentum, which is Vt is equal to beta Vt minus 1 plus alpha times the gradient. So that's the same thing. But what's different is that you don't necessarily take the gradient at Wt, okay, but you take the gradient at Wt minus beta Vt minus 1. Okay. So, I don't think we have to go too much into detail into these Nesterov accelerated gradient. Okay. And, you can, but maybe, let me spend a little bit. So, typically in the momentum update, you have a gradient step, you have a momentum step, and then you actually take an actual step, which is kind of a linear combination of the gradient and momentum step, right? So, for example, over here, right? You're basically taking a linear combination, or actually a convex combination of the gradient and this. Whereas in Nesterov, you actually end up taking the gradient at a different step, at a different point. So for example, in this figure, you kind of take a momentum step and then you take a gradient, which is slightly different than taking the linear combination of the gradients. And you can think of this as kind of a look-ahead gradient step. And in many cases, Nesterov accelerated gradient can actually work better. Although I think its importance has kind of decreased in training large neural networks. Okay. One question is, why does the momentum work? Why is momentum STD better than STD itself? Okay, and remember, let's come back to the root of why we motivated STD, right? Stochastic gradient descent is basically, you can think of it as a way to estimate the gradient. It is an unbiased estimator, right? Which means that its mean of the error at each step can be regarded as 0. But the different estimators can vary in terms of their variance. So their variance might be large for STD, and what momentum is able to do, and you can show it, is that it actually reduces the variance of the gradient estimator. Okay, and then there are some other techniques that people have done over the years, which can actually reduce the variance of the gradient estimator. but momentum is a pretty cheap way. Some of these other methods can have, more computation which is involved, right? So that's one justification, okay? Now let's talk a little bit about adaptive updates. And this is actually very important because many of the methods that are used today in training these deep neural networks are based upon a method called AdaGrad, right? Or you might have heard of Adam, right? So they are somewhat similar, right? AdaGrad, as the name implies, is adaptive gradient. Okay, so what do we mean by adaptive gradient? Okay, let's look at it, right? So what an adaptive algorithm does is each dimension can actually have a different step size. Okay, so remember that my W naught is some d-dimensional model. And like I said, D can be very large. D can be in the billions or hundreds of billions, right? So when I do SGD, the SGD update is the same step size for all the different dimensions, for each of the possibly, 400 billion dimensions. What AdaGrad does is, and I can just go straight to the formula. You can just look at the formula right now. What it's saying is that there should be actually an I over here. I think the I is missing. So WT plus 1 in the ith coordinate is WT in the ith coordinate. And what you end up using is, same thing as before, eta times G. GT just means gradient of F at and the ith component of the gradient, right? There is some notational issues over here, right? So I think I should have probably put J over here, and GJ over here, okay? But what it is saying is that you are taking the gradient and each dimension you are actually scaling by eta, which is as in SGD, but now you have a per coordinate step size. And that per coordinate step size is computed as follows. You take the square of the gradient in that dimension, and you basically just keep on adding it. And then there are some methods where instead of taking them and adding things, you actually again do like a discount factor. You can do beta times GJ t minus 1 plus 1 minus beta times GJ t square. Okay? And this you can actually think about actually as a diagonal preconditioner. So what it is saying is that you take your gradient vector and then you actually multiply it by a diagonal matrix. And this diagonal matrix has these values, 1 divided by square root of GIT in its diagonal elements. And this epsilon is just so that, it's a small constant to try to avoid, things like division by 0. Okay, any questions about this method? So you can basically think of it as, you basically have a step size, a different step size for each dimension. And this can be really regarded as a diagonal scaling of the gradient, where this is the diagonal that you have. Okay. Basically, and if you look at it, right, this has scale of G. This is G square, and you take square root of it. So in a way, this is kind of a little bit like dimensionless. this G divided by square root of G square is essentially a dimensionless quantity, right? So it has, I think, this good property that, for example, if you scale your loss function by alpha, right, this update is actually not going to change, which is actually a good property to have, right? Because in stochastic gradient, if you scale your loss function by alpha, the gradient will also get scaled by alpha, right? And depending upon how you initialize W or so, you might get like, quite different Ws. Either they'll be scaled by alpha or they might actually not be very good. Okay, so this is kind of an important, I think, milestone in training of deep neural networks that, this adaptive scaling is being done, especially when my neural network parameters are in the, hundreds of billions.
May I ask you a question here?
Yes, please.
So is there like an advantage for this method on the gradient descent, not the stochastic? So if you do gradient descent,
Yeah. So, this actually comes under the class of, so if I study classical optimization, right? I
right,
can do gradient descent, and then I can go on to something called second order methods, right? And you might have heard of things like Newton's method and so
right.
on. And they end up also being a scale, changing the gradient direction. And in the Newton method, you look at the inverse of the Hessian. That's
Oh,
what multiplies
okay.
G,
Yep, yep, yep,
right?
yep.
So that is, in the classical optimization theory, that's what happens. And even in classical optimization, sometimes they'll say, hey, like the Hessian is actually a D by D matrix. It's too expensive to compute. It's not only the fact that you have to compute the second derivatives, but it is space inefficient also. Of course, it compensates by, having a faster rate of convergence. Right?
Right,
So the reason it's called second order is because it actually doubles the bits of accuracy. It's supposed to double the bits of accuracy uh, if you are close enough to the solution, right?
right.
And even in classical optimization theory, they will say that, okay, instead of using the Hessian, right, one thing that you could use is a diagonal approximation to the Hessian, right? And in which case, the update actually becomes like this. Wt plus 1 is Wt minus diagonal times the gradient, okay? And then the question is what diagonal you should use, right? Here also, again, computing the second derivatives might be hard, but this is essentially looking at the second moment of the cross moment gradient matrix. So you can form a matrix of, which is GG transpose. And if you accumulate it, then these become the diagonals of those elements, the diagonal of that full matrix. So I guess what I'm saying is that, it's not that this is kind of completely new. It comes out of left field, but it is kind of, related to classical optimization theory. And in the context of neural networks, it's actually an important step because many times you might not have like second order information. It might be too hard to compute. But the gradients are always there. So this is actually easily computed just from the gradients itself.
I
And it
see.
actually ends up having this nice property that it is, like this quantity that you compute is kind of unitless because, like I said, this is G and this is kind of square root of G squared. Did that answer your question,
Yes,
Harmosh?
yes, thank you. Yeah,
Yeah, yeah. Yeah, and I'm actually not going to talk about it, but recently there's also a lot of work in like more general second order methods, right? I actually have done a recent amount of research on it, but there's a method called the shampoo, which uses like a Kronecker product approximation of this second outer product of the gradients, and recently, actually, there was a competition which was organized to find out, so there are a bunch of benchmark problems, and various teams were asked to submit their method to see which method would actually perform the best, right? And they had a particular evaluation measure. And it turned out that, Adam was not the best actually over there, right? Adam is, adaptive momentum based method. So one is difference is that there is momentum over here, right? But then it is similar to the having an um, adaptation over here, okay? And it actually turned out that that shampoo method, which uses um, a more dense kind of preconditioner, which is based on the Kronecker product of the weight matrix or the gradients, is actually a better method. Okay. So again, like lots of like active exploration in this area.
Thank you.
Sure. And then, just to kind of go through again with AdaGrad, right? So for each dimension, we have kind of T samples, GI, from iteration step 1 to step T, and this is each dimension I. Okay, and if you think about like the standard deviation, it kind of scales as square root T. And if you assume that the step size is kind of declining with square root T, then you can kind of do this, right? So as a result, you will notice that this is eta. Okay, this actually does not need to be to decline, because in some sense you can think of it as the actual step size is eta divided by square root T, right? And what you have over here is that you are dividing this G by G divided by square root of T. Okay. And then I think, if you look at current LLM training, probably the most popular method is the Adam optimizer, right? And the Adam optimizer, the name is basically momentum plus adaptive updates. So it has, you initialize momentum, and the notation is slightly different over here. V is actually for the adaptive part over here, right? So you compute the gradient, okay? And then you, a stochastic gradient, right? Then you compute the momentum. So beta 1 times mt minus 1. So you can basically decrease the importance of the momentum or the gradient versus the squared gradients at different rates. So typically there's beta 1, there's beta 2, and then you do this update, which is now, this is momentum, kind of like this, except they have this bias correction term over here. And then there's a little bias correction term over here of the V's. And you basically have MT divided by square root of VT. And VT are the squared gradients. So this is the Adam method that you might have read about in different papers or blog articles, or even if you have run the software and so on, you might end up using the Adam optimizer with different hyperparameters. The hyperparameters referring to beta 1, beta 2, and so on. Okay, any questions? So one thing we talked about is, like what should the batch be, right? At one extreme, you can have a batch of 1, right? But if you think about a batch of 1, it actually has a drawback to it, which means that you're actually not able to use your hardware efficiently. Okay, so we'll think a little bit about that. So the larger batch size implies there is more computation per step, per update. Okay, and it is a less noisy approximation, stochastic approximation of the gradient, right? The current way of doing using deep neural networks is actually very much also tied uh, to the hardware. So I'm sure all of you have heard about GPUs, right? And GPUs are excellent at doing matrix multiplication. Okay, they actually can do matrix multiplication very fast, and as a result, they can fully utilize the computation resource. So what you want to do is you want to ideally for computational reasons, for efficiency reasons, you want to choose your batch size which is large enough that fits in GPU memory and can fully utilize the computation resource. Okay. Can somebody tell me why matrix multiplication is better for using hardware better?
You can like parallelize it with like the GPU, right?
You can parallelize it, yes, that is one reason. But if I have like separate um, matrix vector multiplications or even vector operations, like what is the advantage of matrix multiplication?
I think like the CPU, the GPU, they also have like vector registers, so allows you to like matrix vector multiplication allows you to use those registers. And then
Okay, yeah. So let me ask you a simple question. Suppose I want to take a matrix, which is an n by n matrix, and multiply it with a vector. Okay, how many operations are there? Order to do a matrix times vector operation.
uh it should be O of n squared, right?
It's O of n squared. And how much data is involved in matrix times vector multiplication? You have the matrix, right? So it's n square elements. The vector is n, but you have n square data and you have n square operations,
Yeah.
correct?
Yeah.
Well, now suppose I have two matrices, n by n matrices. What is the time? What is the number of operations that you need to multiply two matrices?
Uh I think I think like it's like the brute force way is like O of n cubed, but isn't there like a faster way to do it in like O of n to like the 2.5 or something, like a little less than O of n cubed?
Right. So let's forget about the faster methods. But the usual way of matrix multiplication, which is actually also in the software, is order n cube. It's about 2n cube, right? N cube multiplications and n cube additions. But how much data is there? How much data is involved?
O of n squared.
O of n squared. So that's the key part. Number of operations is n cube. Amount of data that needs to be moved is n square. So if you can be clever about it, you can actually do order n operations per data movement. That's the reason why matrix multiplication is so much better, okay, on GPUs or even on CPUs, implemented properly, right, than matrix vector multiplication. So when you have larger batch size, you can essentially do most of these operations as matrix multiplication. Does that make sense?
Yeah, now I get it. Yeah.
Yeah. So by the way, you talked about like the faster methods, right? So there's something called Strasson's method that has complexity n to the power log to the base 2, 7, right? Basically, you can do 2 by 2 matrix multiplication, multiply 2 by 2 matrices using 7 operations rather than 8 operations, right? So you can actually get it faster. The problem is that many of these faster methods are not numerically stable. So the usual way of matrix multiplying two matrices is numerically much better than these faster methods. I'm pretty sure that's the only reason why you don't actually see um, uh, these faster methods being used in practice. Okay, otherwise they would actually, if they end up working, it would actually make a huge difference. Okay, so actually I'm still, Strassens is a pretty simple algorithm. I'm not sure why. I think people have tried to make it numerically stable, and I still am unsure why it's not kind of widely used, more widely used. Okay. Okay, but let's go on to, what if I have, for example, now you see about, GPT models, Gemini models being trained with, hundreds of thousands of, GPUs or TPUs, right? Tensor processing units. So how do they do it? Well, they do something called data parallel, right? Distributed computing. Okay, so what they would want to do is you take the total batch size, you increase it linearly with the number of GPUs or devices or chips. And that would be kind of large batch training. Each worker would basically be able to use the same batch. And so that means that if you have more workers, then the total batch, which is the cumulative uh, batches being processed by all the workers, right, will be higher. Right? So that's what you want to do if you want to try to achieve more and more efficiency, if you want things quicker. Right? So of course, like I said, with modern training, not only is so here kind of we have depicted like this master-slave relationship where there's data parallelism. GW from each worker is sent to the master, it's aggregated, W is updated, and W is sent back, right? What is actually done these days in like very large LLM training is that not only do you have data parallelism, which means that data parallelism means that different workers or GPUs can work on different data. But there's also model parallelism, which means that W is actually sharded or distributed across the workers. And typical training these days includes both data parallelism as well as modern parallelism. And it is, like distributed computing skills that makes it all efficient. So that's why it's kind of not really easy to kind of replicate either the GPU hardware or the software that goes to kind of make all these things work. Okay. We've so far talked only about efficiency, right? But actually, what happens to when you have large batch training? Okay. What can actually happen is when you have large batch training, that models can actually end up getting to lower test accuracy when using very large batch size. So there is a point in between where you might have to use it, right? So for hardware reasons, you may want to increase the batch size. But for convergence reasons, you actually may not be able to use very large batch size. And people have done some studies. This is an old study, but it still says that when you use large batch STD or ADAM, remember now we are no longer we are training deep neural networks, right? So we are no longer in the regime where there is just one minima, right? It can actually be the loss surface can actually be riddled kind of with multiple minima and so on. So the study said is that the large batch STD or ADAM actually converges to what's called a sharp local minima, which means that, this is very sharp over here on the right side, right? That you're not in like a very smooth, gradually increasing, gradually, decreasing minima. It's a sharp minima. So as a result, if you just deviate a little bit from it, you actually might get much higher loss values, right? So training can actually end up being a little bit unstable, okay? And so one potential thing to do is that you can actually, as you increase batch size, you can actually also increase the learning rate. And the justification is that, when you look at the variance of the estimator, it kind of scales as 1 divided by B, and you can actually change your learning rate so that it also increases. But the problem is that you cannot kind of keep on increasing it, because for convergence, you can't have the learning rate be too large. So you cannot increase the learning rate without limit. And then what people then also look at is, like, for example, if you have these, deep learning, remember, it's not just neural network learning. Deep learning means that there are multiple layers, right? It's deep, right? So then one can actually try to say, okay, what learning rate should I use for maybe different layers, right? So these are the kind of the different layers of a particular neural network, right? And what one can see is that you might end up having very different norm of the parameters versus the norm of the gradient. So this is an example where if you look at the rightmost column, the norm of the parameters divided by the norm of the updates, or the gradients, sorry, can actually vary quite a bit. So from 20 over here to 3,700. And so what people have done is they sometimes will modify your learning rate, okay, to kind of take out the scale difference. So you can think of it as G is being normalized, and then you scale the answer with, scale the unit gradient with the norm of W. So the updates kind of become similar to the parameters which are being updated. Okay, so there are various methods. One is called LARS, and that's when G is the stochastic gradient. The other is called kind of LAMB, where G is the atom update. Okay, but this kind of scaling is applied. So when it's applied to STD, it's called LARS. When it's applied to atom, it's called LAMB, right? And there was earlier, before the age of LLMs, there were these BERT models that were becoming really popular and influential. Again, this is transformer models. People actually used to use very small batch size, and then it would actually take quite a bit to train it. However, if you start increasing the batch size, training would become unstable, right? So there was a nice piece of work like in 2020 where they used kind of, I think it was either LAM or LARS, probably LAM, and they were able to kind of do this, training the BERT model in kind of 76 minutes at that time. And then both Google and NVIDIA used LAM to train BERT within 1 minute, right? And that all this has kind of laid the seeds to the current LLMs that are being pre-trained. They use just an enormous amount of compute in terms of hardware, enormous amount of training data, and that's how you kind of see the amazing results that you kind of are seeing on a daily basis.